Well, good morning. It's another economics webinar, September 21. It's a little bit rainy here in the Eastern Corn Belt today. I actually haven't looked at the radar. I've been buried in other things this morning, but I suspect it's fairly widespread. It's nothing that's going to be, crazy heavy with regard to precipitation amounts. It's just going to be enough to mess up any desire to get out and harvest some soybeans or some corn this afternoon. Where I'm at in the northeastern part of Ohio, we're probably a little bit away, a little bit of maybe a week away from starting in earnest with soybean harvest. There'll be a few acres that'll start to come out maybe at the end of this week if the weather allows. Just wanted to give you a little bit of a weather update on where I'm at. The topic for today is not the weather pattern in the Eastern Corn Belt or northeastern Ohio. More specifically, it's maybe about something that many of you have probably been exposed to, regardless of your education level. If you've attended an extension presentation conducted by some university representative, and they're talking about experimental outcomes and what we're learning with regard to, let's say, the alteration of seeding rate and how that influences corn productivity. We could do the same thing with soybeans. Or maybe it's someone like myself that's more of a soil fertility trained individual, and they're talking about how nitrogen rate impacts corn productivity, or phosphorus application impacts corn productivity or soybean productivity, or foliar manganese application on soybeans. How does that perform? There's generally some allusion or some statement in the presentation of data that discusses statistical significance. And what I'm hoping to do today is not to make you a statistician. I'm going to expose you to some concepts of statistics. And I hope that it's somewhat intuitive. Because I certainly know, speaking from my own experience when I was in graduate school, taking things like experimental design, statistics 1, statistics 2, you start to see that there is an intuitive nature to how we utilize statistics. Now, if you're not deep into math, it gets very complicated very quickly. I love math. At one point in my career, I considered really focusing on statistics. I never did it. I was much more interested in physiology and chemistry than I was in mathematics, but I recognized that mathematics had a lot of application for my desire to be a scientist that worked in the realm of biology, in the realm of chemistry, and even physics. So what we're going to be talking about today is statistics and variability, what they mean, and why you should care. At the end of the day, when you talk about statistics, you have to realize it is a tool. It's a tool that experimenters use to determine how, I was going to say the word reliably, that's not quite correct, how confident they are in the outcome of an experiment. Okay, in the world of statistics, it probably doesn't surprise you, but everything is couched in the realm of probability. We're not going to make this super complicated today. I say that it's not complicated to me, to someone who may not have much experience with statistics. Maybe some of this is a little bit hard to approach, but I'm hoping that I'm presenting it in such a way that it's going to make sense. It's not going to allow you to calculate sums of squares. It's not going to help you tabulate an F statistic. That's not what we're after today. I just want you to have a concept of statistics, why researchers do what they do. And part of the reason I do that is because, to some degree or another, if you're operating in the ag space, and let's say you're a retailer, you're an agronomist employed by a retailer, and you have a couple of customers that are interested in a specific product. And one of the simplest ways that we can evaluate how well this particular product might perform in my specific geography or within the cropping system, the soils, some of the geographic constraints that we're faced with as agronomists. If I'm trying to evaluate whether or not this has any benefit to my customers, you can do what we call split field trials, right? And part of what I want you to expose to you is, it's not that that's a flawed approach, but it has some limitations. And that's really what I want to try to impress upon you today. So where are we going for this presentation? We're going to provide some fundamental concepts. Again, this is, I've done this presentation in the past. As if anybody's ever seen me present on this, I'm always changing my presentations. So this is going to be a little bit of a different approach than I've ever used before. I'm always tinkering. I'm always hopefully perfecting, I'm using my air quotes, perfecting the approach that I utilize to make the information that I'm providing a little bit more impactful, a little bit easier to approach. So some fundamental concepts of statistics, replication, randomization. Why does replication matter? Why does randomization matter? So I'm going to give you some fairly practical concepts or precepts that will hopefully drive this point home. It's absolutely critical. Then we're going to transition from this concepts, the concepts of statistics, and replication and randomization are the big ones. And then getting into understanding variability. What sort of variability do we experience when we conduct experimentation? And again, I don't care what scale that this is occurring at. You're going to deal with these types of these sources of variability. You're going to have natural variability. We'll talk about that. We'll talk about induced variability. We'll talk about measurement variability or variability that occurs because of some measurement that I'm taking. Okay, everything that's doing a measurement is going to have some level of error. Believe it or not, even the tape measure that you're very familiar with. I don't know if you've ever done this, but that little grippy thing on the end, I'm sure that has some nondescript name that describes it that I'm not aware of. That little thing at the very end where you can hook it onto the end of a 2x4, measure out. If you're trying to cut a 36-inch 2x4 or cut down a 2x4 to 36 inches, that little tab has some play in it. For most of our usage in the world of carpentry, that 1/8 to 1/4 of an inch really isn't that detrimental if I'm off by that measure. But do realize there's much more accurate ways to measure things, right? We can use things like calipers that are much more accurate, but they're much more time consuming. So just understanding where the sources of variability come in, and then getting into the practical side of this. So something you've probably been exposed to, and for those of you who are children of the 60s and 70s, you see the term LSD and you think lysergic acid, I'm probably mispronouncing, lysergic acid diethylamide, right? LSD acid. No, LSD means least significant difference. That's a statistical term. Probably something you've seen when someone presents a data table of information, and there's this number at the bottom, and it's got some like 0.01 or 0.1 or 0.05. And then there's a number that precedes it that's after. It's like, what does that mean? I just want to expose you to what that actually means and how we as researchers utilize that information when disseminating that data to someone who's ultimately interested in, should I be using this product? Should I be changing this practice at the field scale to capitalize on a greater probability I'm going to be able to produce more corn, produce more soybeans, produce more wheat, more canola, whatever the crop of interest may happen to be. So that's where we're going to go. We're going to start with some basic concepts, and I hope that these are, again, somewhat intuitive. If you've never sat and thought about this, maybe it's not. And I do apologize for some reason. Okay, now I can see it. It's weird that it doesn't stay up there. If you do have a question, I will occasionally check the chat, and feel free to throw the questions in the Q&A, and I will stop if I notice them. I'll try to do that every slide is what I'm going to try to do. And if there is a question, I'll try to address it at the time that the question is posed. So the goal of a researcher, what are we trying to do as experimenters? There's a couple things that we're trying to achieve, and I don't know that one is any more important than the other because they both have some level of importance. Number one is to design a good experiment to determine the effectiveness of a treatment or a set of treatments compared to a control or controls. This is critical. This is one of the greater challenges in the realm of soil fertility. When we conduct experimentation and we're trying to evaluate something like phosphorus response, we want to create an environment where the sole, at least ideally, the sole limitation of crop productivity is phosphorus. Well, unless you have access to something like triple superphosphate, which is the 0,46,0 product, it's got no other nutrients in it. If you're using something like MAP or DAP, well, I have to account for that nitrogen. So I have to make some effort to balance things. And that's important when it comes to making sure that we have adequate controls in place so that we're actually evaluating the response that we're after, and it's not confounded with some other factor. Okay, so that's really, really important for us as researchers, and is ensuring that we have an adequate control that we're making our comparison to. And then number two, we're attempting to conduct an experiment to minimize error where possible and establish a fair comparison between treatments. This will hopefully be a little bit more clear as I get into the concept of randomization. Embedded in not so much the first one, but embedded in the second point here is really the concept of replication and randomization that may not be apparent. So let's talk about this concept of replication first, and then we will transition to randomization. So why replication is important, and this is the easiest way that I've stumbled upon to provide a basis for this discussion. Okay, so number one, I used to be an athlete. I still have some athletic leanings. I used to enjoy, I still enjoy watching certain types of Olympic events. It's really weird how your tastes change over time. I'm really essentially only into things like wrestling, the track and field events, and the swimming events. I used to play baseball. I have no interest in watching baseball at the Olympics. And I probably just lost half of my viewers by making those kinds of statements. But the one thing that's always sort of bugged me about events like swimming and the track and field events is you think about like a sprint event, you get one chance. Now you have to go through the qualifiers, right? And then there's usually a semifinal race. But when you get down to the finals, and you can't stumble at any point along this way, or you're not proceeding to the final event. And it always has sort of bugged me, especially when I became more aware of the concept of statistical analysis, is you're allowing these individuals one opportunity to demonstrate their proficiency and ability to run at a really fast rate. They get one chance. The older I've gotten, the more unfair that seems to be, but it is what it is, because they can't run. You think about how long the Olympics last now. If they really tried to set this up to be a fair and statistically valid evaluation of runner performance, well, then it becomes almost untenable, right? Then the length of the athletic event will just be way too long. So here's what we're going to do. We're going to set up an experiment with two fictional people. One's name is Christy, and one is Suzanne. And we're going to let them run a race. So we turn them loose. And for some reason, this is supposed to, there it goes. They run the race, and it turns out that Christy won the race. So in the absence of replication, how many individuals in this audience would be comfortable in saying that Christy is the faster runner? Is that true or false? Well, if I only have one replication, I'm operating on a lot of assumptions. Number one is the assumption that they started fairly when that Christy didn't jump the gun and leave well before the pistol was fired. Not claiming that it was an intentional effort to cheat, but maybe she was a little more antsy, and in the absence of describing what is a fair test, well, she left early, so she was able to reach the finish line first. Or maybe Suzanne stumbled out of the blocks, and she may have had a higher top end speed, but the stumble that she experienced at the beginning of the race was enough to set her back, that even though she may be physically faster than Christy, she wasn't able to overcome the deficit she created for herself with a poor start. Okay, so if you just have one race, recognize there's a lot of things that go into determining what the actual outcome of the race was. And so what do we try to do? How do we address this challenge of other variables that affect experimental, or in this case, the outcome of the race? Well, one way that we do that is we run the race again. We say, okay, to make sure that fluke that we experienced, or to make sure that the experience of the first race was not a fluke, let's repeat it. All right, so we run the race again, and it turns out, once again, Christy prevails. The more times that you see this outcome of the race, the more comfortable you are in making the statement that, in fact, Christy is indeed the faster runner, at least faster than Suzanne. Okay, then the question becomes, well, just how many races do I have to run before I'm really comfortable in saying that Christy is indeed a faster runner than Suzanne? And that's a really important question. It's not something we're going to attempt to answer here today, but just be aware that is something that we're always having a conversation about in the realm of experimentation and statistical analysis. So at least if I have something that's repeated, I'm gaining confidence that the observation that I am observing is not just a fluke, and that there seems to be some validity to the concept that Christy is in fact a faster runner than Suzanne. Well, let's assume we ran this race 6 times, and let's say Christy won 5 out of the 6 races. With that being known, would you be comfortable in saying that Christy was a faster runner than Suzanne? My own suspicion would be yes, I would be fairly comfortable. Now, being more of a statistician and a mathematical person, I really want to see what the difference in the wins were, right? So if Suzanne was losing by like 100th of a second, so of the 5 times that she lost by 100th of a second, but the one time she won by a 10th or a 15th of a second. Well, now I'm starting to think, well, crap, maybe she's really not. Maybe Suzanne is just a terrible out of the blocks. And when she's able to overcome that one challenge, she is in fact faster than Christy, right? So again, that being said, in the absence of the mathematical information or the quantification of that information, if Christy wins 5 out of 6 times, I'm pretty confident that Christy is probably a faster runner than Suzanne. Well, let's change that. Let's say they ran those 6 races and they split those races equally. So half the time Christy won, half the time Suzanne won. Are you as comfortable saying that Christy is the faster runner at this point? Now, again, I'm ignoring any quantitative metrics. That's going to change here in a slide. But if it's a split between who wins, well, now I'm not really so sure who really is the faster runner. And if you pay any attention to, and it's not that I watch these with too great of a frequency, I do like the NBC Sports YouTube channel because I like the Diamond League track and field events that they host, primarily in Europe. And it's interesting how you see different runners come to the forefront. At one venue, it's one runner that wins. At the same pack of contestants, you move to another venue, different time frame, and somebody else wins the race. It's not always the same person that's winning these races. So then that, again, it's bringing up this point, well, who really is the fastest? Is it just at the Olympics every 4 years we determine Usain Bolt is the fastest runner in the world? That may be a true statement, but could we defend that statistically, I guess would be my question. So let's make this a little bit more complicated. So this is all very qualitative at this point. If Christy wins 5 out of 6, yeah, we're pretty comfortable saying that she's faster than Suzanne. But if they're splitting those races and the outcomes are split between who wins 50-50, well, now I'm sort of hedging my bet. I'm not really sure who the faster runner ultimately is. So let's actually quantify this. So of the 6 races, this is the one time. Now, interestingly enough, this is the one time that Suzanne actually won. That was race number 3. So I've highlighted that in red. So on average, Christy is running a time of 10.49. This is obviously not a 200-meter distance. This is probably something closer to 100 meters. So Christy's winning at 10.49. Suzanne is running at 10.49. Suzanne is running at 10.64. Christy won 5 out of the 6 races. If you look at the individual events, it seems to be a somewhat of a consistent difference in the time scale. This one's Christy ran really, really well. Suzanne, either she ran really well or Suzanne ran poorly. But if it's 5 out of 6 and I'm seeing this kind of a spread, I'm pretty comfortable saying that Christy is a faster runner than Suzanne. But then you contrast that with this other scenario here on the right of Christy won the second, fourth, and sixth events, and Suzanne won the first, third, and the fifth. And if you compare the average times that were run by each of these contestants, Christy was winning by 0.04 of a second. So mathematically, the average is tells me that she's faster. But because of the fact that she only won 50% of the time, I'm not so sure that I can put a whole lot of stock in this average number that I see down here at the bottom. This is the quandary that we face as experimenters, is this very thing. How do we quantify the error associated with these different races, and not just quantify the error, but use that quantified error to help us in our assessment of who actually is the faster runner? And that's why replication is so important. If I just had a single observation, if I just saw race 3, you're naturally going to assume, well, Suzanne is faster than Christy. Well, but when you see the other 5 races that occurred between these 2 individuals, you pretty quickly recognize that that was a wrong conclusion. And again, this is part of the challenge of statistical methodology and why we even have statistical methodology. So replicating the treatments, in this case, the races, allows us to quantify the uncertainty of the experimental outcome. This is commonly referred to as error or experimental error. This is one of the primary concepts of statistical analysis is it requires replication. And we use that estimate of error to help us make an assessment of differences due to the treatments, or in this case, differences in the outcome of the races. Now, we're going to discuss error here in a few slides, but replication, or at least the sources of error here in a few slides, but recognize replication is really important. So when I start talking about randomization, I'm going to reintroduce replication in more of an ag environment, okay? Because I've tried to make this something that's maybe I'm hopeful it's a little bit more approachable, a little bit more intuitive, because when you start talking about agriculture, it gets confounded by so many other factors. And I wanted to pick something that's fairly straightforward and simplistic, not simple, but simplistic. So let's talk about randomization really quickly. So let's revisit Christy and Suzanne, at least for the moment. When we start talking about sources of error, we'll force this into an ag environment. Okay, let's say instead of running on a track, right, which is we've all experienced running on a track. I do run occasionally, and I would much rather run on a running track than any other type of surface, primarily because it's so much easier on my joints. That rubberized track has a little bit of spring to it, so it doesn't hurt nearly as bad for my 200-pound frame when I'm bouncing around trying to run at a high rate of speed. But let's say we take them off of the track and we put them on a dirt path. And what we don't know at the beginning of the race is that there's a muddy spot on Christy's path that isn't present in Suzanne's path. So if we run the race, well, Christy didn't win. And the question that we're going to start naturally asking ourselves, especially once we've identified that there's a muddy spot in Christy's lane compared to Suzanne's, is, did that impact the experimental outcome? And if it did, and there's no other place for us to race, how do I account for the presence of this mud on that lane? How would I conduct this race to ensure that Christy isn't being handicapped exclusively by this challenge? Well, let's say we run the race again, but we didn't change the location of the race, the contestants relative to where this mud puddle is. So we repeat the race, and lo and behold, again, Suzanne wins. If you keep these individuals in their same starting positions, and we know that this mud is out there, are you sure that Suzanne is really the faster runner? Even you can replicate this multiple times. And because of the presence of this mud puddle, if you never change the starting position of these 2 contestants, you're going to assume I've got a valid experiment, when in reality, from a replication perspective, you do. But the challenge is you weren't randomizing the position of these contestants on their lanes to account for this challenge that exists in one of those lanes. And I have my first question. Yes, there will be a recording of this that will be made available. It should be posted on our YouTube channel. So if you do have to cut out, or if you miss, as this individual, if you missed the opening conversation, this will all be available through our YouTube channel. And if I'm wrong, Aaron will correct me in the Q&A. So this is why you can't separate replication and randomization, because again, if you're just repeating the race, but you have this challenge in one of these lanes, and I don't randomize the placement of these contestants to make sure that I'm accounting for this impediment to Christy's ability to run in that lane, well, do I have a valid experiment? This is why randomization is so important. You want to randomly select the placement of the contestants in the race. Now, don't be confused. There are other features that we have in the realm of statistics to deal with things like this very thing, right? They're called blocking factors. There are ways that we handle this experimentally. That's not the topic. That's not what we're going to be focused on today, but do realize there are ways that we can handle this experimentally. Okay, so replication, randomization. Sorry, I have to get back on my PowerPoint. Very critical. So if Christy's always handicapped by running through the mud, is Suzanne really the faster runner? We've already discussed this. No, but the way we handle that is we randomize their starting position, and we try to eliminate that bias that is associated with having you run through that muddy area. Okay, so we want to have multiple replications to get us an estimate of experimental error, but we also want that estimate of experimental error to be unbiased. We don't want to have a systematic bias that we have to deal with because we can't quantify it. We just want to try to attempt to eliminate it. And I will concede you can't always do that perfectly, right? Some of the experimentation that I've done in the past, just by the sheer nature of the type of research we were doing, I really don't have the capacity to randomize as effectively as I would desire, based primarily upon geographic features of the field, primarily topographic in nature. Like if you're doing runoff work, it's really hard to do runoff work if you have different slope lengths and different degrees of slope. You really can't randomize. You're sort of bound by the topographical limitations that you're faced with. It makes it a challenge for us experimentally, at least from a mathematical perspective. Okay, so experimental treatments are to be replicated and randomized to get an unbiased estimate of experimental error. If you take anything from this presentation, you have a fundamental basis. If you understand this concept, you have a fundamental basis of experimentation and why we do the type of research that we do. Please include a discussion on value. I will at the very end. That's going to complicate this whole conversation a little bit. It's a little bit more challenging, but at the very end, I sort of get to that point of talking about the benefit cost ratio. And it's really so what we're going to be talking about here is sort of the fundamental concepts of statistics and dealing with variability. But at the very end, Gautam, I am going to make a statement about how you look at data as a whole. I'm not going to get super quantitative because that wasn't the nature, the desire for this particular presentation, but you could certainly do things like cost benefit ratio in determining whether or not a specific treatment or change in agronomic practices results in a good return on investment. That's a whole different conversation. My primary focus today was just going to be on statistics, but I will make a sort of a broader statement at the very end of this presentation that speaks to how do I aggregate statistical information as a whole and generate inferences and make recommendations. Okay, great question. That's a whole other presentation unto itself. So you have a fundamental understanding of replication randomization. Let's talk about variability. So from an experimental perspective, there are deviations in the observations that we're making. And typically we're going to be talking about yield. I'm going to focus on yield today. There's other things that you can measure. I'm going to focus on yield today because it's something that we all understand and it's easier for us to get our heads around. So deviations in individual observations can be caused by natural sources of variability, management, and in an application induced, what I call induced sources of variability, and then measurement sources, right? So again, if you've ever tried to calibrate your moisture meter, calibrate the yield monitor that's on your combine. I come from a lab background, so every piece of instrumentation that I ran daily had to be calibrated every day before I ran any samples through it. Even when you do a really good job of calibrating, and in a lab setting, I can tell you, I can very easily get R-squares of 0.999 with, not for all of the instruments that I ran, but for most of the instruments that I was running, I could get a really high coefficient of determination, which means I'm very, very accurate in the information that I'm capturing. There's still error there. There's still some level of unknown that is induced by the measurement itself. Okay, so the more coarse the measurement and the more coarse the piece of equipment that you're using to capture the measurement, generally the more error that you're going to experience. All right, so just realize these are the three primary sources of error, and I'm going to talk a little bit more specifically about each one of these. So Natural variability, we all have a fundamental understanding of this. If you're involved in agriculture in any way, shape, or form, you understand there are soil textural changes that you experience as you cross the field, right? This is somewhat related to this, but I have areas that are more poorly drained and I have better areas that are more well drained, and the trick question that I often ask is, which one is the most productive? And the answer is, it depends upon the rainfall pattern for the year, right? I can show you, I don't have any of these. I'd have to dig back into my archives of some of my information that I was capturing as a late graduate student. And then when I transitioned into industry, my first foray back in 2003, 2004, where if you look at yield monitor information on the same field in consecutive years, if you have different rainfall pattern, the most productive area in one year can be your lowest producing area in the next. Okay, and most of that is related to drainage. Soil organic matter differences. So not only do I see textural differences, which translate into different drainage, I also have soil organic matter, which can also influence drainage pattern. Bulk density differences, right? I have areas of compaction. I've got landscape position. Am I talking hills at the top of a slope, the side of a slope, or the bottom of a slope, right? Does that influence or cause a source of variability with regard to productivity? And absolutely it does. I throw this in here as a joke, but I had a couple times where I would go onto farmers' fields and try to diagnose why there was preferential silk browsing on their corn crop, and it's just it was on the edge of the field near a tree line, and deer could easily move out into the field and munch on the silks, and then run back into the tree line, and you have preferential deer browsing. Does that influence or cause a source of variability? Pest infestation. There's a number of things that cause that. We could even get into mineralogy of soils in their ability to supply things like potassium, their ability to hold things like potassium, their ability to hold things like phosphorus. That's sort of related to textural differences and soil organic matter differences. Okay, there's a lot of sources of variability. So what does this look like in real life? So this is from a previous life of mine. This is circa 2003, a wheat field in north central Oklahoma. And you can see there's some pretty significant variability. Now, I'm not telling you, I don't provide you a legend to quantify what the differences are between these individual pixels that are representative of different yield levels. So you're just going to have to trust my mathematical ability to interpolate what the yield levels are within these equally sized spaces. So, you know, you think about yield monitor information, you have the ability to go in there and cut out specific areas of known size, and you can make a comparison of yield. And it probably is intuitive. Let me go back a little bit. So if you look at these two areas, this one has a little bit more darker green shade, or at least a higher percentage of darker green pixels. This one has a few more lighter green pixels. So it probably wouldn't surprise you that if you just calculated the yield for these respective areas, there's a 15 bushel difference between these two different areas. And I can tell you on this particular farmer's field, this was not related to anything different that he was doing managerially. At least to our knowledge, right? There could be something that was induced that we were not able to detect. But it just seems like it's a more of a natural variability that existed within this field. So one a little bit, this was circa 2008, 2009 in central Ohio. This is a soybean field. And if I integrate these areas, you look at it visually, it's really hard to see a lot of differences. Some of it is because of the size of the pixels, because of the size of the header, or the size of the head on this particular combine. So 64 bushels on the area on the left, and then 62 bushels on the area on the right. Not a lot of tremendous natural variability between these two areas, but you do notice there is some variability that you are picking up between rows, right? Not rows, but between passes of the combine. Same field, interestingly enough, smaller header, so that's why you have a few more pixels, or a smaller head on the combine. So, and for some reason the numbers showed up, but my areas didn't. Again, not a lot of variability between these two adjacent areas of this field. Great place to do some field experimentation, by the way. There's actually ways that you can do split field research and use this concept of what we call stability analysis over time to help you get a pseudo estimate of experimental error in the absence of replication. But that's a fairly sophisticated approach. But there are ways to do things like that. And this particular field would be a great candidate for doing split field research, because I can, specifically if I have multiple years of like corn and soybean data that gives me some idea of what my expected difference is between these two areas. And then again, using that stability analysis approach, then I can again, get a pseudo estimate of experimental error to compare treatments across these different areas. There's other ways to achieve that, but again, that's not the focus of the conversation today. More natural variability. Now, this is an interesting one. This is this is circa 2008, 2009. And again, this is probably intuitive. A lot of lighter colored pixels here, darker pixels over here. So just looking at this visually, yeah, I'm generally going to expect this to be a higher yielding area than this. And it turns out that visual assessment is accurate on to the magnitude of about 19 bushels difference between this area on the left and this area on the right. What's really interesting is if you look at soybeans in the next year, you don't really pick up much of a yield difference. So could it be textural differences? My inclination is probably not, although I can't say that definitively. Could it be soil organic matter differences? Potentially. Maybe I was a little bit lean on nitrogen, and this area on the left, and this is just me venturing a guess, this area over here having low organic matter, maybe we didn't experience as much mineralization and it didn't have as much nitrogen being released, so therefore it didn't yield as well. And when you put soybeans in that ground, soybeans aren't nitrogen limited, and so I don't pick up much of a yield difference. Again, these are the kinds of patterns that you can start to see. And again, if you have access to your own yield monitor information from the combine, you start to see these kinds of patterns, or maybe sometimes a distinct lack of pattern. And the interesting thing about this kind of information is it's all over the board. I'm just giving you a couple different scenarios. This does not represent the entire breadth of what you would experience. So natural variation is very common. It's, again, something we all understand. I think the induced is something we recognize as well. There's application rate errors, right? I don't know how many times we've done field experimentation and someone didn't have the setting correct on the applicator. Plugged applicators, that's fairly common. Seed skips and doubles, right? Maybe my planner is doing a very poor job of simulating seeds and I'm getting skips and doubles with some frequency. Does that impact the variability that you can experience? Absolutely. Pesticide application errors. That never happens, right? We see it all the time. It's funny driving around in corn or soybean ground early in the year. You see where they had their skips. You see where they missed their applications. Uneven distribution of plant residue. This is maybe a little bit more, well, it's not just specific to small scale experimentation, but it's one of the challenges we have in small scale experimentation is you don't really get even distribution of the plant residue across that entirety of that plot. You're going to experience the same thing at the field scale, right? It's actually going to be worse. You're going to induce more variability because I'm not equally distributing that plant residue coming out of the back end of that combine. It's all going to be applied in a fairly narrow area, unless you have a chopper and a spreader. That causes soil microclimates, right? Where I have a lot of residue, that area is going to be cooler and wetter in the spring. I get poor nutrient distribution, where specifically for things like potassium. So if I'm not doing a good job of distributing that corn stover out of the back end of that combine, I'm basically dumping a lot of potassium in this very narrow strip that's traversing my field. Okay, these are just a couple. And I do have another question, so I'll take a peek at it. I don't know if I would say it to a degree, Gotham, maybe you could say it as mathematical jugglery. But the goal is to be as quantitative and statistically valid as you possibly can be, with the recognition that a lot of things influence the experimental outcome. Our goal is ultimately to try to quantify that variability to the best of our capability and account for it when we're making inferences. And again, for those of you who are maybe a little less statistically minded, that statement didn't mean a whole lot. But essentially what I'm trying to say is we want to assess the error and quantitatively assess it as best we can. There's other things that we can do, right? There's covariate analysis. Now I'm getting way into the weeds. Gotham's dragging me into an area that I didn't necessarily want to go today. But there are ways that we can account for some of these things from a statistical analysis approach. We're just trying to make sure that we're being as honest as we possibly can and statistically and experimentally valid with the inferences that we're drawing. So I want to show you something because this is kind of cool. I did this in response to a question a couple of weeks ago. If this would, there we go. I'm going to jump over to an Excel spreadsheet really quickly. And I hope this is showing up well enough for you to see this. So just this concept of inaccurate, maybe that's not the best word. Imperfect is probably a better one. An imperfect way that we harvest information, whether that's coming from poor seeding or poor measurement. All I really want to show you is based upon some assumptions. Let's just assume I'm dropping 34,000 seeds per acre. I'm operating at 30-inch row spacing. These are calculations that I have to have. My plot length, I can change this. I'm going to keep it at 40. I'm going to keep it, I'll just make it 50. If we're just going to harvest the 2 center rows. So my assumption is this is the traditional small scale experimentation. We're doing 4 rows. We're only going to be harvesting the 2 centers. And if I'm on 30-inch spacing, that means it's going to be a 10-foot plot. I'm going to be harvesting the center 5 feet. I'm making an assumption of what my expectation of yield is. That may or may not be reality, but you're just going to have to accept this at this point. So let's say 230 bushels is what's going to be average, what's going to be yield, what I'm going to yield. Let's say I have a 5% error rate on my seeding, right? How many would be okay with 5%? I think 5% for most of our field equipment, whether that's a planter, some sort of a liquid applicator, I think that's a pretty decent error rate. Well, so if I'm shooting for, if my seed is dropping accurately, I'm going to get 195 plants per plot. But if I have a 5% error, now it's 205. Let's ignore all of the compensatory things that corn plants can do at higher populations and lower. All right, I'm going to ignore those things. Let's just assume that every year is perfectly uniform. And if I have 195 plots or I'm harvesting 205, what would be the potential yield error? If the average is 230, I could see a 12 bushel yield error, but just having 10 extra plants. So let's just decrease that to 3%. Now I've only got 6 extra plants and it's going to change as a function of size of the actual plots. So if I just have 3% error, 6 extra plants, we're talking 7 bushels difference. All right, so let's make it an even smaller plot because I have done smaller plot research. Again, now I've only got 5. I'm only missing, or only have 5 extra or 5 less. I'm operating on the optimistic side. I'm 7 bushels difference. Okay, just that simple thing and it couldn't, maybe it's not just the seeding error, maybe it's the inaccuracy of my plot length estimate. What if I added 4 extra or 5 extra plants into that harvest area for that particular plot? Well, I'm off 7 bushels. Does that affect experimental outcome? Okay, and that's an induced error. All right, that's just a simple illustration of this concept of an induced error from something that we think is relatively accurate. 5 plants doesn't seem like that big of a deal until you actually quantify how much error that ultimately introduces into your estimate of yield. All right, so I'm starting to run out of time, and I recognize that, so I'm going to proceed a little bit faster. I'm not going to spend a whole lot of time talking about this, but just recognize whatever instrument you're using to capture a measurement has a yield associated, or has an error associated with it. So if I'm using a combine yield monitor, there's an error associated with that. It's not an absolutely perfect number. What about your moisture meter? If you don't believe that there is error, I'm a weirdo. I like to track biometrics, so I take my blood pressure every morning, and I take 3 measurements every time I take my blood pressure, and there can be tremendous variability in the estimate of my blood pressure provided by my automated blood pressure measuring piece of equipment. There's variability in everything. Whatever you're using to take a measurement, there's going to be some level of variability. Okay, and again, all we're trying to do is account for that in our estimate of experimental error, recognizing we're not going to do it perfectly. So there's controllable and uncontrollable sources of variability that influence the measurements that we're actually collecting during or after the completion of experiment. And this is why we use statistical analysis. We use this as a way to deal with the reality of variability, and we deal with it mathematically. All right, so let's transition into something that's maybe a little bit more useful. We've got 14 minutes. Should have plenty of time to go through this. This is a real world experiment. So this is not contrived data by me. This is one from one of my PhD students at Ohio State University. This is from his work that's published in his dissertation. If you're really interested, I could tell you where it is. You could actually access the publication online through the Ohio Lab, or the Ohio Library, the Ohio State University Library. So I have treatment 8. There's 8 treatments in this particular experiment. So I'm going to compare treatment 1 to treatment 8. Each of those treatments were replicated 4 times at a single location. So this is just one location analysis. This is rep 1. And what I want you to do is what we're going to do is we're going to compare rep 1 to rep 1, rep 2 to rep 2, rep 3 to rep 3, and rep 4 to rep 4. And we're also going to do a really quick assessment of the variability of treatment 8 across these 4 replications. So my lowest yield was 64.9 and my highest yield was 68.4. Now recognize this is in a small scale experiment conducted at a research farm where we're trying to minimize variability. I still have a 4 bushel difference between my lowest yielding plot and my highest yielding plot. Now my average is 66.7. Contrast that with my treatment 1, the yield variability is even greater. I go from 52.8 to 63.4. So up here, I only had a 4 bushel difference. Down here, I have a 9 bushel difference, okay, or approaching a 9 bushel difference. If you look at how these performed within these different reps, this was a blocked experiment. I mentioned block earlier, but don't get bogged down with this. But compare rep 1 to rep 1. It was a 3 bushel win for treatment 8. It's a, oh wow, that's a 9 bushel win for rep 8 or for treatment 8 and rep 2. I've got an 8 bushel win for treatment 8 and rep 3. Then I've got a 12 bushel win for treatment 8 and rep 4. Now, when you combine these, I'm not showing you the other treatments. All those other treatments are important in the estimate of experimental error. And I come down here to my LSD. So the average yield for treatment 8 was 66.7. The average yield for treatment 1 was 58.2. LSD at 0.1, 3.1. So if these two means are separated by at least 3.1 bushels, I'm 90% confident that the difference between the two is not just sheer random chance and is actually due to a treatment difference. Okay. And I get a little frustrated when people say, well, is it real? 66.7 versus 58.2 is real. Mathematically, they are different. But the question is, how confident are we that the difference that exists between the two is due to experimental treatment or just sheer random chance? And that's really what we're trying to quantify. Okay. So just to give you an idea of what that term, and more so than anything, I want you to have this written down so you can refer to it later. What does that 0.1 and 0.05 value actually means? It gets really complicated. I'm going to simplify it. It's the probability level that we employ as experimenters. So if you read, I've done a fair amount of reading in the medical journals here of late. If in most medical journals, they don't even use a 0.05, they're using 0.01. So they're using a 99%. All right, so what does that mean? So a 0.1 probability means there's a 90% chance that the yields that differ by 3.1 bushels or more are not just different by sheer random chance, with the caveat of a normally distributed population, which I haven't talked anything about normal distribution, heterogeneity or homogeneity of variance. That's all important when it comes to statistical analysis. But for those of us that are practitioners, it doesn't really mean a lot. All you have to recognize is that the typical one that you would usually see from an extension presentation is going to be a 0.1. You will occasionally see a 0.05. So this means 90%, this means 95%. And we're just quantifying how, this isn't technically right, but this is the way to think about it. How confident I am that the yield differences that I see are due to treatments and not just sheer random chance by pulling 2 samples or multiple samples from this population and making a comparison. Okay. Hopefully that provides some clarity on what that LSD and that probability level means. So this is the same experiment actually replicated at a different location in the same year. So I have treatment 8, I've got treatment 1, and I've got my rep. So for treatment 8 across those 4 reps, I've got 8 bushel variability between the reps. For treatment 1, I have got 7 bushel variability. So fairly consistent variability. Compare treatment 1 rep 1, treatment 2 1 rep 2, treatment 3 1 rep, or treatment 1 rep 3, treatment 4, or treatment, goodness gracious, treatment 1 lost in rep 4. So treatment 1 in 3 of the 4 reps. When you do the math, you calculate the mean. Again, what I'm not showing you is in your estimate of experimental error, it's not just these treatments that we are making the comparison with, or when we're determining experimental error, it's not just these treatments, it's all 8 treatments in the experiment. So the LSD at a 0.1 is 3.5. So 56.5 minus 51.7, we're talking almost a 5 bushel difference. So we're confident, we're 90% certain that the yield differences that exist between these 2 different treatments is attributed to the experimental treatment and not just sheer random chance. Okay. And that's how we make that interpretation. Again, I'm just going to show you this really quickly. It's more for you to go back and look at later if you're so inclined. The variability that exists within the individual treatment across the reps that we're conducting the experiment. So we're talking 5 bushel variability. For this one, 232, we're talking 13 bushel variability within treatment 4. Compare the 240 to the 225. LSD at a 0.05, and I'll show you another one in the next slide, what's a different LSD, different probability levels. For me to be 95% sure, they've got to be different by 19.3 bushels. They weren't. So even though this yield level is pretty wide, that's a 15 bushel difference. If I'm using an LSD of at a 0.05 probability level, I can't say that the differences between these two treatments is due to the treatment itself. It could just be sheer random chance. And it's a function of the variability that I'm experiencing. Again, I'm not showing you the entirety of this experiment. There's actually 17 discrete treatments within this experiment, replicated 4 times. Okay, that information is important. But all I'm trying to illustrate here is just because there's a 15 bushel difference, and this makes a lot of practitioners uncomfortable, right? Because you're like 15 bushels to Gautam's question earlier, 15 bushels, well, that should pay for itself. Well, as an experimenter, I'm not confident that that 15 bushels was not just due to sheer random chance, based upon the quantification of error, and again, making some assumptions about normality and things of that nature. So let me show you one more. It's actually the same experiment within a different year. And all I really want to show you with this is when you change your probability level, you change your LSD. So recognize if I want to get more confident, I have to have wider differences in yield, right? So if I'm using just 0.1, all I need is a 9 bushel difference. For the inference for this particular experiment doesn't matter. It doesn't change what I'm concluding, right? These are both going to be statistically different from each other, regardless of what probability level I set. And strangely enough, we can actually tell you what the probability level is. My guess for this is it's going to be approaching 0.01 or something less than that. All right, and just recognize the lower this gets. So if this gets to 0.01, 0.001, the more confident I am that the differences that I'm seeing between treatments is attributed to the treatment itself and not just sheer random chance. Okay, that was enough of that. The last thing I'm going to make here, and then we'll make some concluding remarks here in a moment. Statistics is all about the probability of making a correct or an incorrect conclusion regarding the differences attributed to treatments. Again, our goal is to account for that experimental error, use that in our assessment of treatment differences in order to have some level of confidence of the inferences or the conclusions that we're drawing. Okay, but again, what I have to stress is, in the world of biomedical research, would you want someone using a 0.1 or a 0.2? I've seen people try to use 0.2 probability level. Would you want someone using a 0.1 or a 0.2, or would you want them to be really certain that whatever treatment they're proposing, specifically if it has potential negative side effects, if the treatment that they're proposing is actually due to the benefit that's going to be garnered from doing this treatment is I'm struggling to say this correctly or accurately. If you're talking biomedical research, I want to have as high a probability that this is not just due to sheer random chance. That's the easiest way I could say it. Okay. Now, in the world of agriculture, it's not life or death per se, right? So we can get a little bit looser with this probability level that we employ. I don't know that I've never been comfortable with 0.2, but I have statistical friends that it's always got to be 0.05. Understanding the variability of the nature and the nature of the system that we're conducting research in, I'm okay with a 0.1. So let's put it all together and just a couple of concluding statements, and Gautam, I hope that my next statement will address your point. A well-designed experiment can lead to a meaningful conclusion. That's ultimately what we're trying to do. But remember, the conclusion reached is specific to the conditions of the experiment. I don't know how many times I have to say this, I get really, really nervous when let's say a land-grant university scientist has done 2 field trials and they come out with a statement that we don't need sulfur application in the entirety of the state of Ohio. I'm not picking on anybody. I'm just using that as an example. Well, if you only have 2 experimental outcomes, are you certain that that's going to address the breadth and the diversity of the geography that you're actually providing a recommendation to, right? Because the one thing that we always have to be mindful of as experimenters is the research outcomes are very specific to the experiment itself. The conditions under which that experiment was conducted are critical to what we actually observe. So it has to be a little bit of humility with regard to making widespread, broad recommendations across a very diverse geography when you have very limited research data to substantiate that position. Okay, some humility is required. So how do we address this? Well, this is why researchers, like my time at Ohio State, we conduct research over multiple locations across different years to account for as much of these various conditions as we realistically can, even with the realization we're not going to account for everything. Okay. Now, statistically speaking, we don't have to account for everything. We just have to have a large enough representation of what an individual grower would experience to say on average, and that makes people really nervous. To be honest, it makes me a little bit nervous, but unfortunately, it's the best that we can do, is we say on average, if your soil test level is below 15, 20 part per million Bray-1 extractable phosphorus, or now they've moved to Malic 3, if 20 part per million Malic 3 extractable phosphorus, if you're above that, the probability that you're going to see a response to additional phosphorus fertilizer may be small, but that doesn't mean it never happens, right? So most of the recommendations that we live with are based upon average expectations of experimental outcomes. They don't adequately represent all of the potential conditions that exist within a geography. So take that with a little bit of a grain of salt. So got them to your point, and this is when we do those multiple experiments. So let's say I did 15 growing seasons, let's say 15 site years. Okay, so 35% of the time there was a significant yield increase, at least statistically, using a 0.1 probability level associated with a given treatment. And there was never an instance where yield was decreased that could be attributed to the treatment, at least not statistically. If the average yield increase associated with that treatment was 15%, do you think that's a pretty good treatment for a lot of folks to be considering? This is the way I think about statistics. You look at, I use the statistical methodology to evaluate and give me some confidence in the observations that I'm seeing. But then I also look at how much does it win by and how frequently does it win. There's other ways that we can do statistics. We can pull experiments together to increase the power of statistical analysis. I'm not even talking about that today. But this is the way ultimately I end up looking at statistics is, okay, 35% of the time, it wins 35%. So 35 times out of 100, it wins. And when it wins by 15%. How many like those odds? If there's no potential yield decrease. Now, to Gautam's point, the complication here is what was the cost of it? What's the cost benefit analysis? And that's at a level that I'm not going to get into today because I'm ultimately going to run out of time. Thank you for the questions as we went through. As always, you can use the Ask an Agronomist through our eKonomics website if you have additional questions, you'd like some additional clarification. This was a fun one for me. I am a statistician, so I live in this world still. We still do experimentation. I still get to do analysis. Thank you so much for the attendance. I hope that there was something useful here. Maybe, again, I seem to get the different topics, which is fine. I enjoy talking about these things, as you probably could tell. Hopefully there was some benefit, and enjoy the rest of the week. If you're dry, I hope you're getting some rain. And if you're wet, I hope you're drying out. Take care, everyone.